Hey everyone, welcome back to Matthew 61. This is Scott. Let's get started. The item on the docket today is section 1.9, which has to do with finding matrices for linear transformations. So, matrix of a linear transformation. So in the previous section, we described some the important properties that a linear transformation has to have, and we looked at an important category of linear transformations, and that was what we called matrix transformations. But what if instead of being given the matrix, I'm given a certain kind of transformation, and it's up to me to find the matrix? So that's the idea here. So the idea is we are given a description of a transformation, of a linear transformation, and then our goal is to find a matrix that would do that. So we want to find a matrix to accomplish that transformation. So last time we saw how a matrix could be used to define a transformation, and now instead we want to have a transformation in mind and find a matrix to go with it. So here's our first step along the ladder here. So the identity matrix. So the identity matrix. So the identity matrix of size n. This is a square matrix of a very specific kind. So square means n by n. So this is an n by n matrix of the form we have 1, and then let's see how I want to write this. Let's go 1, 0, 0, 1, dot 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 0, dot 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 0, dot 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 0, dot 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 0, dot 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 1. So we've got ones along the main diagonal, zeros everywhere else. So this right here, little diagonal line going from the northwest to the southeast. This is the main diagonal. So 1 in main diagonal, 0 everywhere else. So for example, if we're talking about the 2 by 2 identity matrix, that's going to look like 1, 0, 0, 1. If we're talking about the 3 by 3 identity matrix, that's going to look like 1, 0, 0, 0, 1, 0, 0, 0, 1. And these always have to be square. They always have to have the same number of rows and columns. They've always got ones along the main diagonal and zeros everywhere else. And so on. Now, specifically in R2, we call the entries, or I should say, we call the columns of I2 the standard basis elements and right. So E1 to be 1, 0, and E2 to be 0, 1. And those who have been around the vector block before may actually recognize these particular vectors, and you may be more used to calling them I and J for the sort of algebraic notation of vectors. So note E1 is equal to I, E2 is equal to J if you have seen that notation before. Now the reason why the identity matrix is called the identity matrix is because if you multiply it by any vector, you're going to accomplish precisely nothing. So note I sub n accomplishes the identity transformation, which means it leaves the image identical to what it started with. In times x is just equal to x. Also, whenever there's no ambiguity, we'll leave off the n. So if the dimension is clear, if the dimension is understood, we often, by which I mean always, omit the subscript. So what that means is I times x equals x. And there's a reason why we use a symbol for the identity matrix that's so suggestive of the number 1, because this is the basic matrix equivalent of just multiplying by 1. 1 is what's called the multiplicative identity, and that's because when you multiply by it, it leaves the result identical to how it started. And similarly here, the identity matrix does the same thing. Now, so that's one matrix that we can get for free, basically. It's the matrix that accomplishes nothing at all. It doesn't change the vector. Now, if we want a matrix for any other transformation, if we want the matrix for any other linear transformation, t from, let's say, R2 to R2, although it doesn't have to be R2, it can be, in fact, Rn to Rn, but we're going to mostly focus on R2 because geometrically it's the one that we can best understand. So if I want the matrix for any other linear transformation from R2 to R2, we can form it as, or we can form it by taking as its columns the images of E1 and E2. So in particular, so thus, if T of x is going to be accomplished by doing A times x, where A is a 2 by 2 matrix, then A is going to equal, first off, the image of E1, and then secondly, the image of E2, and these are the column vectors that you get when you apply the transformation that you desire to the basic unit vectors, the standard unit vectors. As an example, we can take various directions of this. For example, let's talk about a reflection. Reflections. So we can do a reflection about, for example, the x-axis. So that would be taking, so this is, by the way, E1, and sorry, that's E2, and this is E1. So E2 and E1 are just pointing to start off with along the axes. And then when we do the transformation, if we want to reflect about the x-axis, that will be taking the vector that used to be pointing up, and instead now it's going to be pointing down. So that's going to be T of E2. And over here we're going to have T of E1. So those are going to be our two columns, and we can write them as column vectors. So this goes 0 in the x direction and -1 in the y direction. This one goes 1 in the x direction, 0 in the y direction. And so then A is equal to, so the first column will be 1, 0, second column will be 0, -1. Conversely, if we were to reflect instead about the y-axis, then the standard basis elements, E2 and E1, E1 would get sent when we do this reflection to the following. So E1 will be going this way now. Which will be -1, 0, whereas E2 will continue pointing the direction it was, which will be 0, 1. And so what that means is we can take these as the two columns of our new matrix, and that'll be -1, 0, 0, and 1. So what this means is if we want to accomplish a reflection about either the x-axis or the y-axis, so either a vertical reflection or a horizontal reflection, we can do that by actually just applying the rule of matrix multiplication, where these would be the matrices that would accomplish each of these two reflections. So this would reflect all vectors about the x-axis, so it's going to be doing a reflection like that. And this will be doing a reflection of any vector about the y-axis. So that's the first kind of linear transformation we can now formulate by means of matrices. But we can also do stretches. And the stretches that we can do is we can stretch them only in the x direction, or only in the y direction, or we could do a little bit of both, or we could stretch them evenly in both. So let's say factor of k in the y direction. So then we'll take the standard basic unit vectors E2 and E1, and this transformation will now take what was once a vector that only went 1, and it will now stretch it out. So T of E2 would be stretched out by a factor of k only in the y direction. So that what that means is the x direction will still be 0 and the y direction will be k, whereas the unit vector going in the x direction will be unchanged. So what that means is that the matrix in question here is going to be 1, 0, 0, k. Or we could do a factor of L in the x direction. So we can take basic unit vectors. This is J or E2. This is I or E1. And under the influence of this transformation, E2 will be unchanged, but E1, so if that was 1, then it will be out to here, which is L. And maybe L is negative too if it's a transformation that combines a stretch along with a reflection, or if L is less than 1, it would be a compression technically. So here we'll have L 0, and here we'll have 0, 1, and so then we could have A is equal to L 0, 0, 1. And then we could put both of these together and accomplish both stretches simultaneously by putting an L here and a K here, and that would be accomplishing both of these stretches. But you get the idea. Now shears. Now, what a shear refers to is a transformation that goes like this. So what a shear does is it takes we have two kinds. We can have a horizontal or a vertical. And a horizontal shear would take a little unit square, little unit box here. So it's 1 and 1. And what will happen after that will be, after the shear has happened, is the whole box will be squished out in this direction. Where this is still 1 right down, oops, this is still 1 right down here, and this is still 1 out here. However, there is now an extra little shifting to the side by a factor, or by an amount of k. So then, what that means is that the image of the two little unit vectors will get deformed like so. So what once was the standard unit vector pointing in the direction of the the y-axis, E2, will get changed into that, and what once was the standard unit vector pointing in the direction of the x direction will remain the same. So this will become now T of E2, which still goes up 1 unit, but it goes over k units. Whereas the standard unit vector that was lying along this direction will continue to lie along that direction. So T of E1 will just be 1 in the x direction, 0 in the y direction. And so then that makes the matrix equal to, first that column, 1, 0, and then this column, k, 1. Versus a vertical shear, which takes a little unit square and it shifts that into a little parallelogram that goes like so. So once again, we're not changing the area of this. In fact, we're only changing the layout of it a little bit. And here, this is what will be the factor. So this will be the k. And so, if we zoom in on the standard basis elements, we're going to have E2 going that way, E1 going that way, and then we'll do the transformation, and after the transformation, E2 will be stuck in place. So it'll still be equal to 0, 1. However, E1 will now be going this way, which will then be now pointing 1 in the x direction and k in the y direction, which makes the matrix now 1, k, 0, 1. And there are some other some other things that we can do, such as projection onto the coordinate axes, but those are relatively less interesting and less worth our time at this point. But one thing that we can do that is very interesting and very worth our time is a rotation. This is perhaps the most interesting of the linear transformations that we'll be covering here. And it's also the last one. So rotations. So in particular, we're going to rotate we'll say an angle of phi. So this is the Greek letter phi, also commonly written like that. But this is a common alternate way of writing it. Rotate phi radians, and we'll go in the standard orientation counterclockwise. So the standard mathematical orientation is counterclockwise, which corresponds to a rotation from the x-axis towards the y-axis. So you start. So starting here, it would rotate it phi radians that way. Okay, so now let's think about where this would take our precious little standard basis elements. So the default initial starting position of E2 is right there, and E1 is right here. But then if we were to accomplish this transformation, both of these would get themselves rotated phi radians counterclockwise. So what once was pointing along the x-axis is now pointing a little bit off the x-axis. So this is t of E1. And without being able to figure out quite yet what these are, let's just say A and B. And now let's think about the E2. So it gets rotated off of the y-axis the same amount that the E1 got rotated off of the x-axis. So let's think about what this is actually going to be giving us. So these are the same situations. So effectively here, whatever the y coordinate is of this matches the x coordinate of this. So if this was A, then this will also be A. Now as for the x coordinate here, it's going to match whatever the y coordinate was of this one, because these are completely symmetric situations. So this is going to be negative b. Now let's zoom in on this little triangle right here and try to figure out what the A and the B will actually represent here. So here what we've got is a little right triangle with an A down there. This actually happens to still be a 1. We're only rotating it, so we're not changing the length of that particular angle. We've got B over here on this side, and then this is an angle of phi. And then when we look at this, this is actually a classic trigonometry situation where this actually represents the cosine of phi, and this actually represents the sine of phi. So then, what that means is that t of E1 will equal cosine phi sine phi. Meanwhile, T of E2 will equal, and now it's going to be negative B, so it's going to be negative sine phi cosine phi, just going off of what we've got here, which means then that the matrix A is going to look like this. Cosine phi sine phi, so that's the first column, negative sine phi cosine phi. And as an example of this, so this is the most interesting one, so let's try a quick actual concrete example here. Find the matrix that rotates vectors, let's say pi over 6 radians counterclockwise about the origin. So then, here we've actually got everything just the way we want it. So it's just going to be cosine pi over 6, negative sine pi over 6, sine pi over 6, cosine pi over 6. And since pi over 6 radians is the same as 30 degrees, all of you students of the unit circle may well recall what the coordinates are of the 30-degree angle on the unit circle. The x-coordinate is root 3 over 2, the y-coordinate is 1/2. And so we can plug those all in, and that's going to give us cosine, which is the x-coordinate, is root 3 over 2. Sine, which is the y-coordinate, is 1/2. And then we have the same, but swapped and opposite. So this is negative 1/2, and this is root 3 over 2. So this is an interesting fact about matrices. You can accomplish any of these basic transformations by means of a matrix, and that includes something even like a rotation. So if you were doing, for example, something that involved say computer graphics, and you had an image that you wanted to rotate, what you could actually do in order to accomplish the rotation would be to just do the matrix multiplication of the x and y coordinates of all the points in question, do a matrix multiplication by this matrix, and that'll have the effect of rotating the entire image 30 degrees counterclockwise. So similarly, if you wanted to rotate it clockwise, you could just make that negative pi over 6 would be a way of doing that. And so then by that means you can actually accomplish all the rotations that you might want to do of an image in 2 dimensions. If you wanted to make it a 3-dimensional case instead of just 2 dimensions, then actually the matrix would be roughly the same, except you just have more columns. And so you'd figure out what would happen to the unit vector that went along the x-axis, the unit vector that went along the y-axis, the unit vector that went along the z-axis. And then you would just figure out from those, you'd figure out what happened to those based on the angles of rotation, and then you would use those new positions as the columns of your matrix, and that's how you would construct that if it were more than merely 2 dimensions. But for this section, we're only interested really in two-dimensional transformations. So this will cover that. So what we can do now is we can do nothing, the identity transformation, and that's just the identity matrix, which has 1, 1, 0, 0, 1. And then if we want to stretch it in one direction, we can find a matrix for that. If we want to reflect it in one direction, we can find a matrix for that. If we want to do a shear, we can find a matrix for that. And now if we want to rotate it, we can find a matrix for that. So that is how we can construct matrices to match certain transformations. Alright, well that'll do it for this section. Join me for the next episode of Math 261, where we'll be starting a new chapter, Chapter 2. Till then, bye!